So this is the second to last talk for the day, and as you've probably figured out by now, I'm not going to talk about software reverse engineering, but instead we're going to reverse engineer embedded Linux devices. So today we've heard a lot about embedded devices, and this is also an embedded device, but it usually has a bit more power and more hardware. So the outline for the talk is small introduction to these devices, but I think you already know them. Then we'll look at how you can recognize a Linux device and what components are inside of it. We'll try to obtain the firmware from the device and gain root access on the device to further explore the device. We're going to do this in a few ways. And then I'll give you a short introduction on what you can try to do once you've obtained the firmware. And if you pay attention and you apply these techniques at home, you can earn some easy money using strings. So these are the types of devices I'm talking about. I think you recognize most of them. They're connected to the Wi-Fi. They might talk to your smartphone using Wi-Fi or Bluetooth. And in turn, the devices might talk to some cloud provider. Now, I think you recognize a vacuum cleaning robot, a smart fridge. Does anyone know what this device is? So it's a connected AED. So it's a defibrillator. This one has Wi-Fi and 3G connectivity. What could go wrong? Does anyone know what this device is?
It's a dildo.
Yes. So this is it's exactly a dildo. It has a camera. It's already been hacked, so if you want to read more about it, you can go to this link. So Jan Tobias, this one was for you. You should check out this link.
It's a very good starting point,
yeah. So the thing with most of my slides is there will be a lot of links in the slide and at the bottom. The idea is I only have 30 minutes. I cannot discuss everything. So just click on the link and read whatever you're interested in. So this is a slide I borrowed from Frank Piesens about attacker modeling. And we're going to briefly look at these embedded devices and apply his model. So as we own the device, we can observe all of the network traffic. We can send arbitrary requests to the device. And once we gain root, we can also impersonate the device. So send arbitrary requests to the web server. Since we own the device, again, we have physical access and we can access the web server. I also cannot invert hash functions, but I will show you that you not always need to invert them. And again, as we own the device and as we will obtain the firmware, we will be able to reverse engineer all of the client-side code. And as Josep put it in his talk, it's an embedded device, so it is exposed to adversaries in a hostile environment with full physical access and no time constraint. And once you've opened up a few of these devices, you will realize that most manufacturers assume that you will not be able to obtain a firmware and that you will not be able to obtain root access. So this is what most of these devices look like. In the middle, you have a system on chip. This is usually physically the biggest chip on the board, so easy to spot. Then there's some volatile memory, usually DRAM, and you can spot it because it's connected to the SOC using lines that do not go straight. On the other hand, we have non-volatile memory, so this chip stores our firmware, and this is the part we're after. This is a picture of a PCB from a printer. So someone at ASAT decided to leave their printer in the basement, so they abandoned it. We took the printer, we took out the board, and this is what you see. So I think everyone can spot the SoC in the middle of the board. Let's zoom in. So you can see that the SoC is connected to this chip and the lines wiggle to the SoC. So this is the DRAM. So you already know SOC, DRAM, and then those two that are left are flash. You don't even have to Google for the names of the chips. Just by looking at the board, you will notice. This is another board. So again, in the middle, big chip, this is the SoC. Squiggly lines going to the other chips, those are DRAM chips, and at the top we have 8 GB of eMMC flash. So eMMC stands for Embedded Multimedia Card and is basically an SD card on steroids. Now this is a quad-core processor with 4 GB of RAM and 8 GB of flash memory. Any guesses to what this device might be? It's a vacuum cleaner. So there's a few ways to try and obtain firmware from such a device. You could try to sniff the network traffic. This usually works, but I'm not going to discuss this technique. We're only going to look from the hardware perspective. Then the other options are debug interfaces, such as UART and JTAG. Those are the most common. And if those don't work out, we can still take the chip off the board and read it out using a reader. So how do we identify these debug interfaces? Again, the first thing to do is just look at the board. Oftentimes it will be marked on the board, and you can just solder a wire to it, and then you're golden. Another way to do it is to solder wires to all of the test points you can find, and then connect the logic analyzer to it and see what is going on each of these wires. This is the backside of the printer board, and I think you can all spot the JTAG connector on top, so it's marked with JTAG. And then here on the bottom we have two serial interfaces, so one of them is probably the UART interface. So you can solder wires to these and connect them to the correct tool. This is the backside of the vacuum cleaner board, and you can see a lot of test points all over, but in the middle it's also marked, and it's marked using RX and TX, so receive and transmit. This is the UART interface of this particular vacuum robot. So this is what you do. You solder wires to all of the test points you think might be interesting. You can then hook up a logic analyzer to see what is going on. So UART, I've already talked about it. So you need three wires. You need ground, RX, and TX. And this basically gives you a serial console on the device. So in a lot of cases what you'll do is you'll connect these wires and then reboot the device, and you'll see everything what is going on while the device boots. And this will already give you a lot of interesting information about the hardware of the device. Once the device is done booting, there's probably two scenarios that can happen. One is you end up with a root shell, and then you've already won. The other option is that you get a login prompt, and then we'll need to go to the next step. So what you'll often see when you boot one of these devices is you'll see the word U-boot, which stands for Das Universal Bootloader. And it's actually the most common bootloader that you will find in these devices. And it comes with its own command line interface. And this command line interface is usually very helpful because it allows to read non-volatile memory directly or even overwrite it. So what you want to do as an attacker is gain access to this command line interface. Now, if you're lucky and the U-boot is configured incorrectly, then it will even tell you to just hit any key to stop the auto boot, and you will end up in the command line. Now, if the boot delay configuration parameter is set to 0, you will not have this option, and you will have to interrupt the boot in a different way. Now, luckily, there's a few very secret hacking tools for this that you can use, and they're aluminium foil and a needle. So the idea is that U-boot will try to load the kernel from non-volatile memory, and if you interrupt this, you will drop into the command line interface. So with a BGA chip, you cannot directly access the solder balls. So what you do is you take aluminium foil, you fold it a few times, and you just shove it underneath the BGA chip. This will short some data lines, and the kernel will not be loaded. And with this type of package, you can just put a needle on some data lines, and you will end up in the command line interface. Now, this is a technique that's actually well known. You can find a lot about it on the internet, but you never see why this actually works. So this is the main loop of the U-boot bootloader. And you have this call here, and if that fails, so if it fails to load the kernel, it will return, and you end up in the command line loop. Now, there's an easy way to fix this. In your flattened device tree, you can enable boot secure. This is by no way secure boot, but that just gives you another function that does not return if there's a failure. So if this last case happens, then you can go on to JTAG. JTAG stands for Joint Test Action Group. It's an IEEE standard that was originally designed to check if chips are physically interconnected on a board. So you can set any pin high or low and then see if this propagates to another chip. But nowadays, usually this JTAG interface comes with more features, and it allows you to stop the processor, to step over instructions, to skip instructions, to read memory, to write to memory. So basically, if you have full JTAG access and you know how the tab controller works, you can do whatever you want. Now, as I've said, you can solder wires to all of these pins, but to figure out which ones you need for JTAG, there's a few tools. One is a tool made by Joe Grant. It's called the JTagulator. It comes in hot pink, and it will, if you connect the wires to it, it will enumerate all of the possible candidates for the JTAG interface. There's another project called JTAG Enum, and this one you can run on a Raspberry Pi. Now, once you figured out which pins to connect to for JTAG. You can use a few open source tools to talk to the tab controller. Most well-known ones are OpenOCD and Universal JTAG, and there's a few hardware adapters that you can use. I'm not going to go into the details of how JTAG works exactly or how the hardware works, but the links on the slides take you to places where you can read this. So what can you do with this JTAG access? You can bit bang the non-volatile memory, basically. So by using the initial ID of JTAG, setting pins high or low, you can, in a bit banging manner, talk to the non-volatile memory and in that way read it out. This is going to be very slow, but it works. Another thing you can do is you can modify the kernel boot arguments. So you can tell the kernel to boot in single user mode, which basically means that you will end up in a root shell. You can change the root password and then reboot the device in a normal way. And as you can do whatever you want in memory, you can also modify the kernel to your liking. There was also a very recent paper on ARM Coresight. So ARM also adds their own functionality on top of this JTAG interface. And they basically found that they could dump trust zone memory from whatever execution level they had. So they were able to extract the image of a fingerprint from a phone that was stored in ARM trust zone memory. Now let's say JTAG also didn't work, or you don't know how to do JTAG, then there's these options. So we can try to dump the non-volatile memory chip using clips. So this is a SOIC clip, which you can often use for EEPROM chips. They come in all kinds of sizes, and then the other one is a TSOP clip. The annoying thing here is that sometimes the sock will interfere with you reading out the chip, so you'll have to find the reset pin on the sock, pull it to ground to make sure that it doesn't interfere. Then the last option basically is to take the chip off the board and then put it in a reader. So you have a few options. If it's a surface mount component, the easiest thing to do is use a low melting point solder alloy made by ChipQuick. For BGA chips, you can use a hot air station, or you can mill the board from the back down to the solder bolts, but this is of course destructive to your board. This is a short video of how you would do this with ChipQuick. This is the printer board, so one of the flash chips from the printer board. The idea is that you apply the solder on both sides of the chip, and because this solder melts at like 150 degrees Celsius, it also stays molten for longer. You just melt both sides, and then you can push the chip off. This is the eMMC chip from the vacuum cleaning robot. So that one we took off using hot air. And then you have basically two options once you have the chip off. You can buy an expensive reader or a BGA socket to put it in. But I didn't want to spend the money, or I wanted to try it this way. So you turn the chip over, you paste it on a board, and then you solder tiny wires to it. So there's a USB connector on top for scale. There's about 0.5 millimeters in between each of those balls. But this was done using a cheap soldering iron, I would say. So it can be done. You can find the pinouts for most of these things online. And the nice thing about this is actually, so I said it acts like an SD card. And on top you can see that there's 8 data lines, but you only need 1, which is convenient. Another thing you can do is once you take a chip off from one board, you can easily trace where certain lines go on the board. You can then take a second device and just connect an SD card reader to those pins and read out the eMMC flash. So the only lines you need are clock, command, and D0. And this is a regular USB SD card reader. This is another device. It also had NAND flash, but this one had test points for every pin you need to read out the non-volatile memory. So you solder wires to all of those and then connect it to a reader. So the thing on the left here is a reader. Now there's a few kinds of readers. So the one on the left is made in China. It's about 40 euros, I think, and it can read 15,000 different kinds of flash chips. If you want some sockets with it, you pay an extra 40 euros. So for 80 euros, you can read out almost every flash chip you can find. Except for BGA chips. Those are a bit more annoying, so you have special sockets. I think that one is 120 euros for one. And the annoying part here is that you have different types of BGA packages, so different ball arrangements, and then you need a new socket for any of these. So that gets more expensive quite fast. So you now have a copy of the non-volatile memory. So we're going to try to analyze it. In case of a NAND flash chip, the way the memory is laid out on the chip, there's some auxiliary information added by the chip to keep track of which areas of memory are bad. So you want to filter that out first. Now there's tools for that, so that's quite easy. Then once you have the pre-processed image, you can use a tool called binwalk. And binwalk will walk over a binary file basically, and it will try to recognize magic bytes. So headers of files basically. It will report you which files it found, and if you pause it in -E, for example, it will even extract these files. So in that way you will usually end up with the root file system. Now once you have a root file system, this basically becomes a regular computer. So you can look at the files as you would do on your Linux machine. So you can look at a few interesting files. etc init.d will contain all of the scripts that are run on startup. And this is interesting to figure out what the device is doing, or what it's doing when it starts up. etc shadow contains your password hashes. I'll give an example of those later on. hostapd.conf is a configuration file that stores Wi-Fi credentials. So for example, the case of the printer can connect to Wi-Fi. If you then dump the printer somewhere and some person extracts the flash memory, you might go and look at this file and obtain your Wi-Fi credentials from your place. You can look at environment variables, and you can use strings and grep to search in binary files. Another thing to do is to emulate firmware. So a lot of these devices have a web interface. So what you can do is you can use one of the emulators to emulate this web interface, and then you can not only interact with the web interface, so test the website like you would normally do, but you can look at the source code at the same time. So this is an example of a vacuum cleaning robot. So we took off the eMMC, we read out the chip, and we looked at the contents of etc shadow, and this is what it looks like. So it starts with $6, and that means that it's a SHA-512 hash. Then there's a salt, and then there's the actual hash. Now we could start guessing random passwords or use a dictionary to brute force this, but this might take a while. So we looked a bit further on the device, and we found this script, which is basically run when the device is provisioned. And as you can see, they generate a random password, which is nice. But the way they do it is they call OpenSSL round hex 4. And this basically means give me 4 bytes of randomness, and they will be in lowercase hex. And of course, knowing this, it's a lot easier to brute force this password. So we can use a tool called Hashcat. And Hashcat has a lot of highly efficient implementations of hash functions with implementations for GPUs. And we happen to have a machine with a quite powerful GPU. So it was able to brute force this password in about 2 hours, 2 hours, 48 minutes. So the mask you can see here is basically the pattern I tell it to search for. So lowercase hex characters. This machine has 2 GPUs, one fast one slightly less fast one, and it was able to test 200,000 passwords a second. So once you have this password, you can log on to the vacuum cleaner over SSH, and your root, of course. Now I told you I was going to tell you how to make money doing this. So there's a few companies that offer bounties for bugs you find in their hardware devices. I think Ubiquiti Networks offers the highest bounties, up to $25,000 for a single bug. These are usually remote code execution for the highest values. These are only the public programs. There's a lot of companies that have a private program, and the idea is that once you find a bug in any of these programs, you get invited to the private ones. My experience is that if you find a single bug in any of these, they will send you an email asking if you want a certain device to test. So these are some bugs that I found. So this was a Wi-Fi connected device. it has an Android app to talk with the device, to control it. And what the app does, it fetches a config file from a remote server that contains all of the update URLs. I think we've mentioned SSL pinning during the course this week. This app did not have SSL pinning. And the firmware updates are not signed. So you can make your own update server, make your own version of the firmware, DNS spoof the app will download your config file and will send your malicious update to the device. I cannot tell you which brand of device it was because of the rules, but it's a brand you all know, so it's not that difficult to find this type of bug. Same device, I looked at etc init.d to see which processes it starts. And then what you usually do is to run strings on these binaries to figure out what they're kind of doing. And scrolling through these strings, I found a few things that looked like SSIDs and passwords to me. Now there's a great website called wiggle.net, and it's basically a big database of all of the SSID credentials or SSIDs over the world. So it has a database of 500 million SSIDs. It also has Bluetooth devices in there. You can search for an SSID and it will show you on the map where it knows that this SSID exists. So by doing this for the strings that I found in the device, I knew that I had the Wi-Fi credentials for the development environment of this company. This is a different device. So they were using U-boot, but they had modified it. So I requested the source code because it's a GPL licensed open source project. And this board not only had non-volatile storage in the form of flash, but it also had an EEPROM chip. And this EEPROM chip contains basically configuration settings. Now what the system did was to read this chip on startup. So what I decided to do was just fill it with random crap. And I noticed that the device just crashed immediately at startup. And the reason, I had the source code, so I could even point out the exact line where they made a mistake. They were using sprintf, which is an unsafe C function. And this gave me full control over the link register in Arch64, which basically means it's a classical stacked buffer overflow like Frank Piesens mentioned. And this is nice because in this case, the manufacturer decided to implement their own kind of secure boot, but this vulnerability happens before they even check anything. So you can disable secure boot. So this is what this looks like. So when the device crashes, it prints all of the contents of all of the registers. And this screen is whatever I wrote to the EEPROM. So you can see that the link register contains EDBD, and that's the same thing that I circled here, but it's in the reverse order because of the endians. Okay, that was it for my presentation. If you have any questions, then I'll be happy to answer them.